Well, not that okay. So here we are in week 14. We're almost done. Do we have a quiz this week? That's a good question. We probably have a quiz. Let's have a quiz on Wednesday. All right, let's have a quiz on Wednesday. We haven't had a quiz in a while. And we
On
have
what?
a number of quizzes. No, I mean, I would have made a quiz before the end of the semester anyways. Just if we have it now, we don't have to worry about it next week. So we'll talk at the end of the class today what it will be on. But for now, we are now in week 14. We have today, we have Wednesday, we have next Monday, we have next Wednesday, and we have the following Mondays. We have 5 days to go before we're all done.
Oh my God.
And we're going to be working today on chapter 19, which is sampling methods and sampling distributions. So if you've ever made anything to eat, like soup, then you probably, you put in some ingredients, you start heating it up, maybe it's for a big party. You want to determine whether or not the soup is ready, or whether or not the chicken's ready, or this is ready, or that is ready. So what do? You take some soup and you taste it. But you don't take a bigger spoon because it's a bigger pot, right? Assuming that the soup is mixed thoroughly, the same size spoon is going to work for a bowl as it will work for a pot, as it will work for something that size in the picture. And this represents the fact that when you are sampling from a population, when you have the entire population in front of you and you're taking a little bit of it to sample to determine something about the whole population, you don't necessarily need a huge sample as long as it's mixed thoroughly. What is the mixing thoroughly referring to when it comes to sampling? It's referring to random samples. Okay, we don't want to have any bias in our samples that will skew the results. What's an example of a biased scenario? What if I was interested in everyone's favorite sport? So I decide to ask people, hey, what's your favorite sport? And where am I going to go? Well, I'm going to go to a Lakers game next week. So next week, I'm going to ask everyone at the Lakers game that I come across, hey, what's your favorite sport? That seems, hopefully intuitively, that it's a little biased. People at a Lakers game might not necessarily love basketball more than any other sports, but there's a propensity to enjoying basketball if you're at the game in the first place, correct? So we call it a biased sample. So when you take a sample, you want to make sure that your sample is not biased in one direction or the other, but that it is purely random. Okay, and we will talk about how to take a random sample. And there are books on sampling. There are courses on sampling. There are PhD theses on sampling. It's a big topic, which we're going to touch on just a little bit. So the basic idea of the reason why we take samples in the first place is because when we take a sample, we want to take information from the sample and infer information about the population. So for example, if I'm interested in the average height of every American, what if I go to every CSUN students and I ask everyone in CSUN for their height and I take the average of all the CSUN students? Now, how many Americans are there? There's something like, what, 400 million or something like that. And how many people are at CSUN? Something like 40,000. It's a significantly small, it's not even what is it, a percent? Less than a percent. It's like a 10th or 100th of a percent. But yet somehow, if I get the result from the 40,000 CSUN students, I'm fairly confident that the true value is somewhere near there, right? Because CSUN students don't have a reason for having tall people. It's not like a basketball school, or short people. It's not like a jockey school, right? It's just a school. There's tall people, there's short people, there's medium people. On the average, it should average out, and the people at CSUN are no different than everywhere else. So it's a good sample, okay? And we can infer information about the population from the sample. For another example, is in the last few months, we've had, of course, the political climate's been pretty big recently. And there are probably lots of polls that you read about on either in the newspaper or online or you saw on TV. Oh, Biden has a 8% lead or this or that or whatever. Well, they didn't ask me and I vote. In theory, they didn't ask you necessarily. I mean, anyone here actually been asked in a poll who they vote for? And yet somehow they're saying that, so-and-so is going to win because 8% of Americans or whatever the case may be, right? So the question is, how can we infer information about the entire population from the sample? So that process is called statistical inference. And that's going to be the main topic of the next few chapters, okay? But the key idea is to randomize, okay? You have to pick your sample in a random way for you to be able to take the information from the sample and apply it to the entire population, okay? So there's some vocabulary that we're going to be using when it comes to sampling, and these terms are going to pop up so often that we kind of highlight them and make sure that we're all on the same page when we talk about them. So the first one is the population. The population is the set of people or objects that you want to know about, okay? If you're interested in who's going to win the next election, your population is not all Americans, because not all Americans can influence who wins the next election. Your population is going to be the voting Americans, because those are the people who actually have a say in the matter. I don't care what the homeless people, no offense to them. That's a bad idea. Bad idea. I don't care what children think, because children have no say. They don't vote, right? That doesn't matter. What matters is the voting population. That's my population. If I am interested in, well, like the picture shows, suppose I'm interested in Skittles. Now, I don't know anyone who's not interested in Skittles. Maybe it's Solara because she's on this stupid, crazy diet thing that she's on. But everyone else is interested in Skittles, right? Everyone loves Skittles. Okay, it's just one of the, Megan, we love Skittles. Stop shaking your head. Okay, we all love Skittles. Oh, someone's texting.
I agree with Blair. I don't like Skittles.
What was that?
I agree with Blair. I don't like Skittles.
Okay, you guys are excused. I just don't want to see you right now. You're bringing me down. Okay, you're bringing me down.
Skittles.
Huh?
Okay, so Blair's right. No, Starburst is way better than Skittles. If we're talking about
good too, I'm not saying Starburst is
I agree.
Starburst is way better. I hate Skittles. It's just there's something about them. I don't like them.
Down with
They're
Skittles.
just kind of sour to me.
You know what?
He's so upset.
Anyways, okay, so the population of the objects that we want to know about, the units or the cases are the actual individuals in the population. So it could be every starburst in existence. It could be every Skittle in existence, or every, I don't know, every person, every voter in America, every car in America. Of course, you know, every case is different, but we have the units. Now, the population is different than the population size. My class yesterday or last week had a very difficult time with this. The population is not a number. The population are the objects that you are investigating. The population size is how many objects there are. They are different. This is a distinction. If I say, what's the population of Skittles? You don't say 16 million. That might be how many there are, but it's not the population. The population are the Skittles themselves. The population size would then be 16 million. I just made that number up. It's probably a lot more because everyone loves Skittles. Anyways, moving on. Now, a parameter is a numerical summary of the population. The two major numerical summaries that we're dealing with in our class are the mean and the standard deviation. The population mean is a summary of the entire population. The population standard deviation is a summary of the entire population. The population interquartile range, the population range, the population 25th percentile, the population this. Anything that applies to the entire population is a parameter. Now, most samples don't get the entire population. Most samples get only a small portion of it. Tomas, what are you doing?
I don't even know how he did that.
Sorry, I don't know. I'm actually zooming from my phone this time, and I usually do my laptop. And I'm like, what is this pen thing down here? And it was like clicking random stuff. So I'm sorry. I'm like trying to navigate it through my phone.
Okay, maybe you can take over my job. Actually, Solaire's already taken over half my job. You can have the other half.
I'm sorry.
A census is when you collect data on the entire population. The plural of census, whatever that word is, don't occur very often. In fact, does anyone know how often America takes a census? God damn it.
Every 10 years?
Every 10 years. And it's actually a federal crime to lie on a census. Okay, they take them very seriously. Yes, they take them very seriously because it's a government form. It's a federal crime to lie in a government form. They take them very seriously. Censuses, whatever the word is, can help direct government policy. depending on various demographics and how many households and this and that, etc., they can actually affect government policy. You lie upon that, you are skewing the data. They put a lot of money into a census, okay, a lot of money. The sample are the units that you're actually studying to infer something about the population. You take a sample of people, you get something from the sample, and you infer it about the population. Again, the sample are the actual the units that you're studying. The sample size, different, is how many units there are in your sample. Now, when you take your sample and you get an estimate, the estimate is then the numerical summary of the sample. Okay, every sample is going to have its own numerical estimate, and we're going to use that numerical estimate to infer something about the entire population's parameter. Remember, parameters go for the population, estimates go for the sample. Now, if I take a sample and I get a value that I'm trying to estimate, its chances are not going to be exactly the same. Even if I took every CSUN students and was able to average their 40,000 heights to get their average, chances are their average is not going to be exactly the same as the true average of all Americans. So there's going to be a sampling error. The sampling error is the difference between the estimate and the parameter, and it's called also the error due to sampling. It's not that you made a mistake. It's not that kind of error, like, oh, let me correct that. Okay, the process itself lends itself to making an error because there's no way to get a perfect value unless you take the entire population. Does that make sense so far?
Mm-hmm.
So since we all do love Skittles, let's do an example of Skittles, and don't say anything if you disagree because I don't want to hear it. So 20% of all Skittles are red. This is a fact. This is a fact. Okay, we don't argue on this. Okay, it's the 11th commandment. 20% of all Skittles are red. Now, in front of us is a random sample of, I don't know, 15, whatever number that is. We'll have to calculate in a
There's
minute.
13.
Okay, someone already did calculate it. I actually knew the answer, but I wanted to hold off until I answered that question. But thanks for ruining it. I appreciate that. So, in fact, since we've already ruined it, which question did you just answer on this page with the answer 13? Which of these questions did you
The
answer?
population size?
No, that is not the entire population that we're looking at. This is just our sample.
Got it.
Sample size?
Sample size is 13. Hello, dinner. Thank you. Hello, oh, the wire. Okay. So I'll have to go tomorrow to pick the thing up. Okay.
If you're going out.
Yeah. Sorry. So
Wait, Professor.
what was that?
That's why you wait a little bit, Professor.
I'm sorry. Just I haven't eaten for 2.5 hours, so I'm hungry. Okay, so the sample size is 13. I don't know how to layer fast for like long time. I can't go more than like 2.5 hours. Like food. I need
I
food.
skipped through half of it, so
Well, that's cheating.
nope.
All right. So, anyways, the sample size is 13. What's the actual sample? What is the sample?
Skittles.
One Skittle?
It's these Skittles. Now, the sample is that whole thing. These guys, this is my sample. It's those 13 Skittles that I happen to have in my hand. That is the sample. Now, the population, on the other hand, is what?
All Skittles?
All Skittles. And what is a unit in this case?
One Skittle.
Hey, yeah, one Skittle. Or that's a weird word to have like in singular tense, right? Because nobody ever eats just one Skittle. You always have more. So it's like Pringles, right? You can't stop eating them. So what is the unit? A Skittle. Now, what is the population size? This one's a tough one to answer.
Millions.
Yeah, I mean, I have no idea what it is. It's some huge number, right? I mean, how many Skittles are in existence? I mean,
Google it.
you can probably Google it. They probably tell you how many Skittles are made per day and how many bags are sold per day and how many come per bag. I mean, you can probably figure it out.
Oh my God.
If you took 13 Skittles from like a bag of Skittles, would that bag of Skittles be your population size?
No, that's your sample size.
So according to Google, it says 200 million Skittle candies are produced each day.
What a world we live in. Yes. Okay. 200 million per day. And we've been around a lot of days. So that's a lot of Skittles.
When
Huh?
were Skittles invented? 1974. So times 200 million times the number of years they've been around.
That's amazing. Now you got to take into account how many were eaten. And,
Yeah.
you know, and how many like are under the couch, because you know there's some are behind the couch cushions, you know. You do that little cleaning once a year and you find like all those Skittles and you're like, oh, these still taste good. You know that thing I'm talking about? Anyways, so moving on. I'm kidding. We'll just say a lot. I don't know, right? We'll just say a lot. Now, in this case, what is the value of the parameter?
Did you want to?
Huh?
Mm,
What's the value of the parameter in this case?
Would we know that since we don't know the actual population size?
We don't know the population size, but the thing that we're of interest to in this study, we actually do know because they gave it to us. It's 20%,
20%, yeah.
right? 20% of all Skittles are red. And in our random sample, we have 3 red Skittles. So what is our estimate for the percentage of all red Skittles?
Was that 3 divided by 13?
Exactly. 3 of our 13, which is what approximately?
I'm doing it. 3 divided by 13 is 0.23.
Oh, wow, it's about 23%. Which is not exactly 20%, but if you think about 9,200,000,000 Skittles, that's a huge amount, and I probably had half of them. All right, so
Professor, I have a question.
yeah.
How did you get 3 for the estimate?
Because if I looked in the picture, I saw that there were 3 of them that are red,
Oh, okay, that makes sense.
right? Or they actually told me 3 of them are red. Right?
Okay, wait.
Yeah.
There's only 5 colors of Skittles though, right? So is that like every Skittle color is 20%? Or is there just a specific number for red only?
That's a good question. I don't know. I don't think they make the same of each kind. I don't think they do. I don't think they do, because you know what? They probably do studies on people's favorite colors, people's favorite taste, those people who enjoy Skittles, which is the majority of us. And they probably want to have a proportion that is in line with that. Because who wants to buy a bag of Skittles and have like all the colors that you don't like? So Lair, what's the answer?
there's 20% of each of the 5 colors.
Well, there we go. Okay. So
Nobody likes grapes.
through that. Okay. Well, I like my idea better. Anyways, what is the sampling error in this case?
Is
Would
it
it
that?
be 0.23 minus
same amount?
0.20?
Yeah, the estimate minus the
The actual
Parameter.
parameter gives us a sampling error of 3%, which isn't too bad. Right? That's not too bad. Okay. So let's scroll down. We're going to skip this. We're going to skip this. We're going to skip this. Ooh, this looks like fun. Let's not skip that.
Oh my God, what is that?
Okay. That looks fun. Let's see what it says. I mean, it might not be fun, in which case we might skip it after all, but we'll take a look. Okay, class activity. The 100 rectangles on the next page are numbered 1 to 100. So there's 100 rectangles here, and each one is labeled 1 to 100. Do we agree?
Mhm.
Okay. I mean, you probably didn't look at every one of them, but let's assume it's correct. For example, rectangle 40 has an area of 8 square units. So let's find rectangle 40. Okay, where is rectangle? Oh, it's
At
right
the
here.
top in the middle.
Here's 40, right?
Mhm.
And 1, 2, 3, 4, 5, 6, 7, 8 square units. Okay, so, okay. Your goal is to estimate the average area of all 100 rectangles using a sample of size 5. Okay, in other words, there's 100 rectangles, but you're going to pick 5 of them. What I want everyone here to do right now is, as best you can, randomly pick 5 numbers from 1 to 100. And you write them down. As best you can, randomly pick 5 numbers from 1 to 100. Okay. And it actually makes no difference which 5 numbers you pick because there's no order to them, right? So you can, in theory, do 1, 2, 3, 4, 5. Does everyone have 5 numbers?
Yes.
Okay, what I'd like you to do now is I would like you to find those 5 numbers and calculate the average of those, calculate the area of each of those 5 rectangles and take their average.
Where is 21? I can't find 21.
I think I actually just passed it. It's
21.
it's in the like it's right here.
Oh, hang on.
To what? There's a little circle. Oh, here we go. 21
Yeah,
right,
it's a 1 square.
Oh, huh. Okay, thanks.
21 right there. Actually, it kind of looks like the numbers are, I mean, the screen is sideways, but right to left, the numbers drop.
Oh, okay.
Yeah, how's that diet with your focus going now, huh?
I found all my numbers actually, so.
That's why you asked. Where's 21? Oh, it's like right after 20.
Can we plug these in the chart?
Well, you're going to calculate the area. Well, the chart's not big enough for the entire class. I want to kind of like get an idea of what all of our samples gave us. I mean, we have like what, 30, 40 people? So everyone should have, so you should have 5 rectangles, calculate the average area of those 5 rectangles.
Okay.
Has everyone found their rectangles?
Yes.
Has anyone not found their rectangles?
Me.
Popsicle, you want cheese?
Which rectangle are you looking for?
21.
Right here?
21 is a 1 unit, so the area is 1.
How do we calculate the area again?
Huh?
Length times width,
The number-
so side by side, basically.
The number of squares. The number of squares is the area.
Are we just calculating the average areas of what we found?
Yeah. So you have 5 rectangles. You're going to take the average area of those 5 rectangles.
Okay.
Oh.
Okay. Now, when everyone to do, we're going to do this further quickly, but I would like everyone to get their value, to get their average. Does anyone yet not have their average? Because we're going to need it, everyone to have it for me to do what comes next.
Did anyone find 78?
Yeah, 78 is right here. Right there. You got it? It's 4.
Yeah, I got it.
It's 4.
Thank you.
You're welcome. Okay. Going once. If you don't have your area yet, say something in chat or verbally. Going once, going twice, going 3 times, sold. Okay, so what I'm gonna do now is a little different than what they have here. Oh, let's use a dot plot. Okay, so I'm gonna make a dot for each number for area. Remember, this is for the average area. And I'm gonna go quickly, so I need you to be ready to either speak up or to type in something when I get to your number that you just calculated. Okay, so going 0, 1.
I got 1.
You got 1 as your average,
I did 1 through 5.
and all 5 of them were 1?
Yeah. Same.
Oh, okay, fine. All right. So how many people got 1?
Me.
That's
I got 1 as well.
So 2 people got 1. Okay.
3 actually. I saw Monica was on there.
Okay, so 3 people got 1. Okay, 2 as the average. 3 4, 5.
Me.
I got 5.
Okay, how many 5s is that?
There's people in the chat. It looks like 1, 2, 3, 4. Oh my God, it's moving. 1, 2, 3, 4, 5, 6.
I
One.
got 2 4s and 2 1s.
Well,
There's
But
2 more
that-
4s and
wait. 2 4s and 2 1s. What do you mean 2 4s and 2 1s?
of my areas.
No, but you got to calculate your average area. Only one number.
Oh, okay.
You average your 5 numbers.
Tomas asks if we're rounding.
Yeah, round. Yeah.
I believe there's 7 5s because there's 6 in the chat, and I have one. I think Taylor has one, right?
Okay, 4, 5, 6, 7. And someone had, she said 2 4s and 2 1s, but it's only 4 rectangles. What was your 5th rectangle? Hello, whoever you were. Hello. Okay.
It was
Well,
Brianna.
Brianna, was that you?
Yeah, I'm finding my average.
Okay. Meanwhile, 6.
Me,
Yeah.
I got 6.
Okay, that's 3.
yeah, that sounded like
Okay.
people.
7. 8.
I got 7.
Got 7. Okay. 8.
Me.
Okay, we got an 8. 9.
I have 9.
Okay, is that 1 9?
I think that was 2.
2 9s. 10. 11. 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 24, 25. I don't think any of them were that big. What was the biggest? Oh, there were some bigger ones, but on average, it'd be very tough to get them. So it looks like if we actually look at our dot plot, what's the mean approximately?
5.
Yeah, I mean, probably
4, 5.
point something. Probably 5 point something, right? Because there's certainly more data to the right side. But why don't we calculate the median? Because this is skewed. So let's calculate the median instead.
Professor, I'm confused.
Yeah, about what?
How to find the average of the area of the rectangle?
Add them up and divide by 5.
Okay, that's what I thought. It was 4.4.
So we'll go to 4 on that one. Okay. Whoops. So 4, right there. Okay. So this tells us that the average or the median, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So about 9, 4, 5, 6, 7. Yeah, so the average is, if we take the median because it's skewed data, it looks like the average is about 9. Sorry, about 5. About 5. Okay, so what this tells us is that our sample got a value of 5. Now, what is the true value? To get the true value of all 100, what would I have to do?
Add them all up.
I have to add them all up to find the total area. Now, I don't want to do this, and I'm not going to. And do they give us the answer? Here we go. So the distribution below shows the areas of all 100 rectangles, and they have an average of 7.4 square units with a standard deviation of 5.2 square units. So our value was roughly 5, a little to the right of 5. So our value of, let's say, 6 wasn't really that bad. It wasn't horrible. Now, if I asked you all to take another 5 and to do the same exact thing, what would the result be, do you think? Will we get exactly the same numbers that we got the first time?
No.
No. Okay. But I would still expect, with the size of the class that we're dealing with, I would still expect for the average to be roughly in the same place, even though the details are a little different. Because when you take a sample, your sample average and the actual average are usually going to be close together. Okay, you're sampling, assuming it was a good sample, your sample average, your sample mean, and the actual mean are gonna be the same. or in the same, roughly the same. Now, could I get a really bad sample? Well, some of you did, not intentionally. Some of you picked 1, 2, 3, 4, 5 and got an area of 1 as an average area, right? Okay, and that's a perfectly valid sample. And that just illustrates the fact that some samples are going to give values that are a lot further away than other samples. The point that we're trying to make here is that just like a regular distribution has multiple possibilities, right? If you look back at the normal, it's probably going to be in the middle, but it could really be here or there, it could be anywhere. So too, when you take a sample, are you going to have lots of possibilities? So we have what's called a random sample is going to have its own distribution. Now I want to demonstrate this in a different way. I'm going to pause sharing for a second. Okay, I'm better, right?
Yeah.
So it's this one right here. Okay, so what we have here, okay, is we have, this illustrates the central limit theorem, which we're not going to worry about. But essentially, here's the main idea of the central limit theorem.
Are you supposed to be sharing right now?
Am I not sharing?
No.
No, that was not what I intended.
There you go.
Okay, so here we have the central limit theorem, something about the central limit theorem. And again, if you are not familiar with the central limit theorem, don't worry about it. Essentially, what we're going to do is we are going to pick 30,000 numbers, approximately 30,000 numbers between 0 and 100. And we're going to do it with different possible distributions. The number 5 you should recognize. What's number 5? What kind of distribution is number 5?
Normal.
Normal.
That's a normal distribution, which means the majority of the data points are going to be in the middle. And you're not going to have too many data points on the far left or the far right. And in fact, if I do it, what do I see? I see a histogram that resembles exactly what I expect. So not exactly what I expect, but pretty close to what I expect, right?
Mm-hmm.
Okay, yeah, it's not exactly perfect because this is an actual simulation that we're doing. And in an actual simulation, it's never going to be exactly perfect. If I did another one, it would be in the same boat, but not exactly the same as the first, right? Every one that I do is a little bit different than the one before it. Correct? You agree? Am I on the same page here?
Yep.
Okay, now let's do it one that's maybe less familiar, like this one. This is called the uniform distribution because every number from 0 to 100 is as equally likely as any other number from 0 to 100. Now, if I were to do this exact process for the numbers from 0 to 100, where everyone was equally likely, what would my histogram or my bar graph look like?
Flat.
This one.
It would be what? I'm sorry? So, what do you say?
Oh, I don't know. I said a flat line.
Well, let's take a look. Is that roughly what you expected?
Sure.
Right? It's basically saying that each possibility is as equally likely as the next one. And therefore, we should expect to have roughly the same amount per number, and we do, right? And if I did it again, I'd have exactly the same result, right? Not exactly the same result, but in the same ballpark. And if I do something weird, like let's say number 3, which says you're very likely to have a small number, you're somewhat likely to have a large number, but you're not likely at all really to have a middle number, then how many of each do I expect to get in that scenario?
Basically what it shows in that little mini graph.
Well, let's see what happens. So let's draw it. Is that what I got?
Mm-hmm.
That's exactly what I got, correct? Now, here's the beautiful thing. What if we take averages? What if we take averages? In other words, I don't say take 1 at a time, but rather take 2 at a time, or 3 at a time, or 4 at a time, or 5 at a time. It's not going to look the same because for 1 to be here, that's not a problem because they're the most likely, right? But for the average of 2 to be here, both of the ones that I picked should be here. And that's not as likely. So if I increase my sample size to 2 and do 2 at a time, I get a different graph altogether. And if I do 3 at a time, it's different again. And if I do 4 at a time, different again. And 5 at a time, different again. But what's happening as the number goes up?
It's becoming a normal distribution.
It becomes a normal distribution. Let's look at one like number 4. I do 1 at a time. I get a result that kind of looks like what I expect. 2 at a time.
Sure.
Yeah.
So are you averaging those distributions with each
No.
other?
So what I'm doing, like when I say do 3 at a time,
Uh-huh.
what that means is I want you to do 3 numbers from 0 to 100 and average them, and that's what you're going to plot. So like if I go to this one here, this number 1, okay? If I pick 1 at a time, it's very likely to be here on the far left, very likely to be here on the far right, and very unlikely to be in the middle. So I get a data like this, right?
But when you go into your app that you're doing right now,
Yeah.
you're saying you're doing 1 at a time, but that's for 4. But if you do 1 at a time for like 1 or 1, how do you know which one to
So
do?
Wait, it depends. I'm just doing examples. Every example, I mean, these are just examples to illustrate the idea.
so
So
just
what's the idea here?
The idea
Yeah.
is, well, the idea is as follows. The idea is as follows. Your original distribution is what it's going to look like if you take 1 at a time. So if I take 1 from something that looks like this, it's very likely to be on the left. It's very likely to be in the right. It's not so likely to be in the middle. So I get a graph that kind of looks like that, correct? But if
Yes,
I average them, if I take 2 at a time and average them, well, let's think about this now for a second. If you average 2 numbers that are very likely to be in the far left or far right, you should expect a lot of averages right in the middle. Right? If you take lots of zeros and lots of hundreds, then on the average, you're going to get a lot of 50s, aren't you?
Professor.
You hear what I'm saying? One second.
Yeah.
You hear what I'm saying?
No. Yes, I guess.
So I expect to get lots of zeros, which means if I take 2 numbers at a time, I expect lots of them over here, lots of them over here, and lots of them in the middle. Let's see what I get. And if I do 3 at a time, and if I do 10 at a time, what happens is the distribution changes. Now, what happens the difference between 30 and 25 and 20 and 15? What do you notice about these things? They're all normal, but there's something different between them. What's the difference between them?
How close that the data is centering in the middle?
Not exactly. Here's 15, which is centered right in the middle. There's 20, which is still in the middle. There's 25, which is still in the middle. There's 30, which is still in the middle. What's the difference of all those?
I mean, they're accumulating towards the center.
Well, they're all centered in the center, right? But the spread gets smaller.
That's what I mean.
Yeah, the spread, even if we start with normal, okay, here's normal at 1. If we go up to 30, it's still going to be normal. But look how tight that one is now.
Professor?
Yeah.
Just to clarify, so every time you're increasing the sample size, can we imagine it as you take a certain number as your sample, and then you go back into that same population and you go again and you take a sample, and then you average sample 1 and sample 2 together?
No. Each of these bars represents a different possibility for what you get from your sample. You don't average the samples. You plot your samples. Every one of these, well, this is 1 at a time. But if I were, oh, they don't even have it here. Okay, so never mind that one. This is 1 at a time. But what we did when we did this one up here and we made our dot plot,
Okay.
we didn't average our samples. We just plotted all of our samples, didn't we?
No, we averaged it.
We
No,
took
no,
the
no, no.
average too.
Your sample was an average. We didn't average the samples.
Okay, so we have a sample that's the average.
Yeah, every sample is itself an average, but we didn't then go ahead and average your sample and my sample. We
Okay.
plotted
Okay.
your sample and we plotted my sample. We plotted all of the samples.
Okay.
Okay, each sample was an average, but we plotted all of them. And then we saw what this shape looked like. Ours looked a little skewed when we plotted our sample of 5 at a time. It didn't look like this one, which is 1 at a time. Right? When we did 1 at a time, we see some 16s, we see some 18s. When we did 5 at a time, we didn't get anything past 10.
Oh, I think I get it now.
Okay, 5 at a time has a much different look than 1 at a time.
So the 5 at a time, 1 at a time, you're taking 1 unit at a
Yes.
time?
Yeah, 1 unit at a time, and you're plotting each possible unit.
Okay. So
Okay.
for that first graph that looked like a V, where it's very likely to be low, very likely to be high, that is if you take 1 unit out of that entire sample.
Correct.
So then when you upgrade it to 2, if you take 2 units out of that sample, the distribution changes because there's more.
Well, so let's take a look. If I have 1 at a time, I'm going to get lots of zeros and lots of hundreds. Right?
Can I ask a question really quick?
Go ahead.
I'm not really understanding the whole 1 at a time, 2 at a time. And also I'm not really understanding what you're doing in comparison to what we just did.
Let's say you have 100 objects in front of you, numbered 0 to 100 or 1 to 100. Pick one at random. Just pick
Number
one.
15.
No, I'm saying don't pick one in your head at random. I'm saying pick an object at random from 1 to 100. Okay. You're going to plot that on your bar graph. You're going to say, okay, I got one, tick mark. Okay. So for example, in this case, I have 32,967 people picked a random number from 1 to 100.
Okay.
And I got about 1,000 people who picked 100, and a little less than that who picked 99, and a little less than that who picked 98, all the way down to not very many picked 50, and lots of people picked 0. Okay, so at 1 at a time, my very weird looking shape looks like this. You know why? Because for some reason, 0 and 100 are very popular numbers, and nobody likes to pick 50. Okay, so in that case, we have very few numbers here in the middle, and lots of numbers in the beginning at the end. What's an example of this? What would be an example in real life of a scenario where lots of small numbers and big numbers pop up, but very few middle numbers pop up? A real random scenario in nature. How about accidents, car accidents per age of driver? You're going to have lots of accidents for people who are 16 through 20, right? As you get older, the number of accidents people have goes down because you get better at driving, you become safer, right? And then you reach a certain age and now your reflexes start to decline a little bit and the number of accidents goes up again. So this is an example that I just came up with of something that might have a shape like this. But you know what? It's a pure mathematical example, so I don't care what the actual situation is. I have a problem where if I pick one number at a time, I'm going to get lots of zeros, not very many 50s, 25, somewhere in between, and so on. That's just 1 at a time. Now, suppose instead of picking 1 at a time, I take 2 at a time and I average them. So Soler, everyone, Tomas, everyone. Do I expect lots of zeros when I pick a number from this distribution?
Yeah.
Okay, which means if I pick lots of numbers, I'm going to get 0, 0 lots of times, right? Okay, so when I average 2 very small numbers, what am I going to get?
The midway between.
Yeah, the midpoint, which will be a very small number. Right? The midpoint, which will be a very small number, correct?
Right.
So if I pick 2 at a time and I average them, I still expect to get lots of small numbers. And I still expect to get lots of big numbers because I'm going to get 100 twice. You know, I'm going to get pairs of 100 or 99s and so on. So I'm going to get averages that are really big as well, right? But now let's think for a second. I also expect lots of pairs of numbers to have a small and a big number because there's so many smalls and so many bigs that if I pick 2 at random, chances are I'm going to get lots of smalls together paired with lots of bigs, correct? And if I then average those numbers, what is that going to be approximately?
In the middle.
In the middle. So I
The
expect
middle goes
lots
up.
of numbers here, lots of numbers here, and lots of numbers in the middle if I pick two numbers at random and average them and plot. And sure enough, that's what I get. So there.
Just to reiterate, using the example of the areas of the squares that we just did,
Yeah.
so each of us picked 5 random numbers,
Okay.
and we got our average because we did calculate we calculated the average to be around 5 something, right?
Okay. Yeah.
So if we picked 6 next time, our average would maybe move closer to that real average of 7. And then if
It
we
should.
picked 7, and then if we picked 8. So is that what this is showing?
So this is showing not just that the average might move, but that the shape changes
With the more samples
with
that
the
we take.
larger sample size. The shape changes as well. And
And so
although we haven't gone this far in the book yet, not only does it change, it gets more normal the bigger the sample is.
And so for ours would be like where you're putting the number up, it would be 5 because we took 5.
So we took 5 at a time and averaged them. So yeah, so for mine, so if we go back to the page, and this is the sample. So this, I'm not sure, none of our 8 samples would mirror this necessarily.
Maybe that squiggly one.
But isn't this 1 at a time that you just said?
Maybe number.
Yeah, but none of these 8 mirrors the 1 at a time. Right? Does any of those 8 mirror this shape?
Well, we could pretend.
Okay, let's pretend it was 6. So that when I draw 6, I get a shape that looks like that. If I do 5 at a time instead, I just get a different shape. Okay, even something weird looking like, let's say 8, which is very likely to be on the far left and very unlikely to be here. I do 5 at a time, it's going to look normal, which is a property that we'll get to later. The point is for now that when we do random sampling, we have a sampling distribution. A sampling distribution means that the number that we get, the shape that we get is going to be different for a sample than it will be due for the whole thing. Does that make sense based upon what we just did?
Mm-hmm.
Okay. So random sampling will be in the Common Core. Okay, so how do we do random sampling? So if I wanted to pick 5 people from this class at random, just randomly pick 5 people. If you were actually in a class, would I be able to do this? You got to look at me for this one. You, and you. Is that random?
No, it's not.
It's not even close to being random. Because I would never, in a million years, pick 5 people that are next to each other if I did it that way. Right? Because if I said you, and you, 5 in a row, people would be like, wait, that's not random. They were next to each other. But to be random sample, any group has an equal chance of being in the sample as any other group, which means it's just as likely for 5 people who are next to each other to be picked as it is for 5 people that are spread out.
That's why teachers put names on a stick and put it in a cup.
Yeah, so the best way of being random, put everyone's name on a piece of paper, put it in the hat or whatever, and pick them at random. That is, and shake it up. Because if you do that, any n people are just as likely to be chosen as any other n people. 5, 10, whatever your size is, right? Any are just as likely to be chosen as any other. You can do it on a card. You can have, you can do random digits. I can give everyone a number between 0 and 35, whatever number of people in the class, and then go to a random number generator and just pick the first, 5, whatever. Right? So there are ways of getting random numbers, a random sample.
Wait, can you go back? I was still writing the random digit.
Oh, sorry.
Thank you. Sorry, I'm a slow writer.
Don't worry about it. Just tell me when you're ready.
Sorry, I'm almost.
Take a picture with your phone.
I did, but I usually forget to look, so I'd rather just have it written down.
It's okay. It's all good. Can I go now?
Yeah, you can.
Okay. So let's do this one. On a slip of paper, write yes or no to this question. Have you surreptitiously looked at your cell phone today during class? Now, I can speak for myself. I didn't even hide the fact that I did. Okay. I looked over my phone like 12 times. Okay. I can't go more than 3 minutes without looking at my phone and seeing who's texting me and whatnot. That's my own problem. Right. Okay. Because I am addicted to my cell phone. Okay.
I had to look up what surreptitiously means.
That means you're trying to hide the fact that
Secretly.
yeah, in secret. You know, you're trying to hide the fact that you're doing it. It's like,
Oh, okay.
you know, something like that versus just, oh, okay. And then you come back. I do that all the time. I'm, you know, that's my own problem. I probably shouldn't, but I do. So have you surreptitiously looked at your cell phone today during class? Then it says draw a random sample of 12 slips. So suppose we all answered yes or no, and we put it in the thing, and I put everything in the hat, and I picked out 12. The proportion that said yes would be my sample estimate, right? Because I didn't look at every slip. I only looked at those slips of the 12, correct? So chances are that my estimate is not going to be the same as the one for all slips, right? It might be coincidentally, but probably not. In this case, what is my parameter? It's the true proportion of all people in the class who looked at their cell phones versus my estimate, which is the ones that I checked, or, you know, the estimate of the ones that I checked. What's my sample size in this case? We can actually answer that one based upon what's on the page. What's my sample size?
12.
12. The sample are those 12 that I checked. The population is everyone in the class. The units are the people in the class. The population size is the class size, right? These are all things. I don't know what they mean by census here because, I mean, I guess technically we did check everyone, but I don't know what they're asking for here. But we can certainly calculate the sampling error if we did this group activity, which is the sample estimate minus the parameter.
Wouldn't the census be the whole class because you're only picking 12 out of it?
Yeah, but that's also the population. I don't know what
Do
they
you
mean
do
by
census based on population or no?
Well, the census, as anytime you look at everything in the population, it's a census. So it is a census because I checked everyone in the class in this step here, examine all slips. I did check everyone. It's just like, what am I supposed to write here? It's just, you know, it's just, yeah, okay, check. It is. Moving on. Okay. So this is the idea that what I was illustrating just on the other thing, a sampling distribution. When you take a random sample and compute a summary statistic, such as a mean, the statistic is going to vary depending on which sample you got. My sample and your sample are probably not going to be the same, right? So we have what's called sampling variability, right? It's not going to be exactly the same because there is sampling variability, okay? Now, what we created is an approximate sampling distribution. It's an approximate sampling distribution because we didn't check every single possible sample, right? We all took a different sample, presumably, unless magically two of us got lucky and picked the same 5 numbers. Although some people did say 1, 2, 3, 4, 5. So that wasn't really so random. But in general, right? In general, your sampling distribution is going to look very different than the population one, as we saw on the applet. In fact, this is the one for every single sample of size 5 from the area problem that we did earlier. And what do you notice about that? It kind of looks normalish, right? It kind of has a normal looking shape. Agreed? Yes, no, maybe so? You all with me?
Yeah.
It kind of has a normal looking shape. And what's the mean? What's the mean of this?
Somewhere 7-ish.
Approximately 5.
Yeah, here's 6, here's 8, so somewhere 7-ish, right? Seems reasonable. Now the population mean was 7.4. That's what the population mean was, 7.4. What is the sample mean approximately? Well, if this is a sample distribution, it looks also to be around 6.8, 6.9, 7, around there somewhere. Same area, correct? Roughly the same thing.
Yeah.
Well, by the way, what was the largest estimate of all the 5 size samples? Which one is the largest?
16?
16. And what's the smallest?
Like almost 1.5.
About 1.5, 1.4, give or take, something like that. Right? The largest and the smallest seems reasonable. What was the largest sampling error? Out of all these 5 size samples, with all of their values, which one is the smallest error? Or the largest sampling error?
16.
Well, 16 is not an error. That might be the value of the estimate. That's not the error.
How do we state that again?
Well, what's the formula for the sampling error, which I gave you earlier?
Oh, estimate minus parameter.
Estimate minus parameter. So the estimate is 16. What's the parameter? It says it in the problem. What's the parameter? I mean, it's right there. What's the parameter?
I'm blanking.
Right,
5.
literally says it right there. It's the only number in the bottom of the page. It says the population mean is this.
Oh,
It tells us right there what the parameter is. So anyone, what's the parameter?
7.4.
7.4. They give us the parameter. They tell us the mean of the population. So what is the largest sampling error?
what is it? 16 minus 7.4?
That's
8.6.
Huh?
8.6.
8.6. The largest sampling error is 8.6. Now, if you took a sample, is it possible that you would get an error of 8.6?
Maybe.
Possible? Yeah, maybe, right? Because one of them is 16. So it's possible you get an error of 8.6. Is it likely that you get an error of 8.6?
No, because you only have one
You only
sample
have
at
one.
16.
In fact, what's the most likely error of them all?
7.
The most likely error is 7? That means you're around 14.4 most often?
Maybe like
Oh,
2.
no.
Is it like 2-ish? Up to 2?
I'd say the most likely error is around 0. The peak of these is right around 7.4, isn't it?
Right.
Right, where's the peak? Where's that big one that's in the middle? 6.
Well, wouldn't 0 minus 7.4 be negative 7.4?
Why 0? What do you mean? This one right here is about 7, isn't it?
No, that would be 7.4 minus 7.4.
This one here is 6.8. So what's the most likely error?
0.6.
Negative 0.6. Right? Our estimate minus the parameter, correct?
Right.
So our most likely estimate is 6.8, which means our most likely error is negative 0.6. What's your confusion?
Can you restate that again? So you're saying, okay, so we're saying
Most likely estimate is here, 6.8. That's the most likely estimate. It's the one that occurs the most often. It's the one right in the middle.
okay.
Okay, so if I get 6.8, my error is negative 0.6.
6.8. Oh, because okay.
Right? My sampling error minus my parameter is about negative 0.6. So that is the most likely sampling error.
So you would take 6.8 minus 7.4 and that'll give you negative
Negative 0.6.
Okay.
Okay, because my sampling distribution is centered at 6.8 approximately, which is very close to 7.4. Now, how can I get it even closer to 7.4? By doing what?
More samples.
Taking more samples.
Not more sample. Well, we have all the samples here of size 5.
Increasing the sample size.
Increasing the sample size. taking
Okay.
samples of size 6, taking samples of size 7, taking samples of size 8. The higher the sample size, the more accurate will be your data. Okay, so we can skip this one because it's just redundant. This is redundant. Okay, let's do this one here because it's an important one. Despite knowing how dangerous it is and despite the laws against it, 3/4 of drivers who own cell phones admit to texting while driving. Admit to it. Now, if 75% admit to it, how many do you think actually do it?
100%.
Quite a lot.
Probably. I know I do, and I'm not necessarily saying this is I'm proud of this, but I do. So probably about 99%. Suppose you take a random sample of 50 drivers who own cell phones and ask them if they text while driving, and 42 say yes.
Wow.
Well, there's no wow. This is just an example. Okay. So what are N, P, and P hat? So N is the size of your sample. What is the size of your sample in this example?
50.
50. P is the true value of the proportion. It's the parameter. What is the true value, according to this problem at least, of P?
3/4 of 50?
No, 50 comes from our sample. Our sample cannot be used to tell us the true value.
Oh,
The true value is just outside of our sample. The true value is 75%.
yes.
75% of drivers admit to texting while driving. Bam, that's the true value. Now that might be inaccurate as a true value, but for this problem, it's a true value. 75%, that's the true value. Yes?
Would we write P equals 0.75?
Yeah, P equals 0.75. That's the true value. Now, P hat, this little symbol on top is called a hat. P hat is our sample proportion. In our example, what is our sample proportion?
Would it be 3/4 of 50?
No, nothing to do with 3/4. Nothing to do with 3/4 at all.
42 out of 50?
42 out of 50. In our example, our sample proportion is how many successes we have over how many trials we had. 42 said yes, 52 were asked. So our value is 42 over 50, which equals what?
0.84.
0.84. Now, is 0.84 in the vicinity of 0.75?
Sure.
Sure. Which means, what's our sample error going to be?
0.09?
Yeah. Hold on, someone texted something. What was N? N is 50. It's our sample size.
Maybe 0.09.
So 0.09, right? 0.09 is our
Sample error.
value minus the true value. Right? Our estimate minus the proportion, minus the parameter. Okay. Now, which of these is the best picture to represent our sampling distribution?
Would it be A?
Why
The first one?
Tell me why A.
Well,
why did you select the one that you did? So why A?
Because 75% said that they text while driving. That looks like it's pretty much 75%.
So very good. The reason why it is A is because we know that the true value is 75%. So we expect that our sample should be centered at the same point. And this one is centered at 75%. This one's at 60%, which is way off. This is also centered at 75%. But this one's saying we only got 1 or 0.75 or 0.5 or 0.25 or 0. Here you can get lots of values, and each of these different values is a different possibility. You can get 1%, 2%, 3%, 4%. Well, actually out of 50, you can only get evens, but 2%, 4%, 6%, 8%, and so on. Now.
Hey, Professor?
Yeah.
Going back to the A, section A, What is the estimate and which one's the estimate and which one's the parameter?
This is the estimate, p hat 4,250. That's what we got from our sample. What we got from our sample is the estimate. What the true value is, which they gave us, that is the parameter, that is p.
Oh, okay, thank you.
Okay, so we have our estimate and then there is the parameter. Now, here's an example where they did some poll. I don't really care what it is, but one of these is a sample of size 4, one's a sample of size 10, and one's a sample of size 40. And the question is, which one is which?
Maybe the largest of 40 is the one in the middle. 10 could be the first one and 4 could be the last one.
No, but thanks for playing. Oh, wait, I'm sorry. I had it backwards. Yes, that's exactly it. Sorry. I was so ready to say you were wrong, but you were right. Remember what I showed you? The larger the sample size, the tighter our sampling distribution is going to be. So 40 is very tight. 10, not so tight. 4, even less tight. And notice how, because the average they're telling us actually is 1.1, we expect our centers to be right around 1.1, which they are. Okay. As the sample size increases, the sampling distribution of the mean gets more normal in shape. We showed that, right? It gets more normal in shape. The mean stabilizes, right? This one gets more normal. The mean stabilizes while the variability does what? Shrinks, goes down.
Professor, can you go over this problem again? So we're looking at families of size 4, 10, and 40.
Right.
What
So
are we looking at in the graph wise though? Like where does it say 40?
it doesn't
Or-
say 40. 40 is our sample size. We're saying one of these 3 bar graphs comes from taking groups of 4 at a time and averaging 4 at a time. One comes from averaging 10 at a time, and one comes from averaging 40 at a time.
Oh, okay. So then
more that
40
you
would be the
did-
one in the middle.
Yeah, the bigger your sample size, the tighter the tighter your distribution is going to be.
Okay, that makes sense.
If I took a
Thank you.
huge sample size, it would get really tight, and I would know my value, which is why we take bigger samples.
Okay.
Is that
thank you.
true for every sample?
As a general rule, yeah. Yeah.
Okay.
Okay, so this is perfect timing. It's 8:14, 8:15. I'm going to stop recording.